Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step 1 inside is we have arrived at the concluding section in Chapter 6 in the Big Ideas Math Integrated Math 3 textbook, Section 6.5 on solving rational equations. What we just did on multiplying and dividing, and then adding and subtracting all lead to this, especially the adding and subtracting portions of them, because finding a least common denominator and things like that still apply, but now we actually solve for those variables. We can never divide by 0, so what originally x could be in the denominator, make sure those solutions don't work. Those will be extraneous. I'm sure those will pop up here, among other tricky things. I know that they do, so I hope we don't have to graph so much again like we had to do last time. But jump to the description section down below if you'd like to find the PDF of this textbook thing and anything else I need to provide. Maybe graph paper. We'll see what I have to provide for you, as well as get your graphing calculator ready, anything like that. Let's go ahead and get started with the lecture portion and find the timestamps and playlist down below if you want to find anything special based off this stuff. We are going to solve rational equations by cross-multiplying. Interesting. They never really have used that phrase in the past, even from like IM1 and IM2 days. Solve rational equations by using the least common denominator and use inverses of functions. We've done inverses before, but I guess this is for rational functions. This is where they want to do them because this is equations this time. Yeah, cross-multiplying is a new thing. I was stuck on that as I was reading the rest of these here. Cross-multiplying tends to be something that I think books try and not say just because of the magic step of what they are, but once we kind of learn how they work, I guess we're all good with it. I'm good with it if you're good with it. Don't make a mistake on when to use it, when not to, and how to. You can use cross-multiplying to solve a rational equation when each side of the equation is a single rational expression. Basically, when you have a proportion set up. This over this equals this over that. So this is an example of solving this. By cross-multiplying, we multiply 4x plus 5 up with 3 and x plus 1 up with 9, and then boom, you have no more fraction. That's the essence of cross-multiplication. What we're actually doing is we're multiplying both sides by 4x plus 5, which it cancels here, multiplying both sides by x plus 1, which it cancels there. And then you solve for x. So you distribute here and you do your solving, you get x equals -2. Now, you should double check this. I don't think you have to substitute because that's what they're doing here. They're substituting to make sure left side equals right side, and that's all good and great. I'm not double checking to see if the left side equals the right side. I'm double checking here to make sure that -2 wasn't a domain restriction value. My domain restriction values would have been -1 and -5/4. So as long as x isn't one of those things, you're good. So -2 should be fine. Just kind of keeping that in mind. That's the first example. That makes me think our first problems will be proportions where we solve. Something that you might have done since IM1. I'm not really sure. Second example, writing and using a rational model. Okay, we're actually solving, maybe because it's still a proportion, we're doing word problems here next. An alloy is formed by mixing 2 or more metals. Sterling silver is an alloy composed of 92.5% silver and 7.5% copper by weight. Didn't know, now I know. You have 15 ounces of 800 grade silver, which is 80% silver and 20% copper by weight. So I guess 1,000 grade silver is 100% silver. Is this then 925 grade silver, I guess? How much pure silver, that would be 1,000 grade silver, should you mix with the 800 grade silver to make sterling silver? Okay, so they're going to, I was going to do something different. They're going to talk about the copper and leave the same amount of copper in as a result. So here's what they're doing. They're saying the percentage of copper in mixture is the weight of copper in mixture divided by the total weight of mixture. So one version of this they have on this side is 7.5 over 100. Now you can also write that as 0.075. That would be the decimal equivalent of that percentage. Nothing wrong with it. So you might wonder why they didn't do that the first time. I guess number 1, to make it look like a proportion, and number 2, so you can make sense of how to write this other side. What they're doing on the other side here in my book, if they're doing 20% copper, if you have 15 ounces of something that 20% of is copper, 20% of it is copper, I should say, then you multiply 0.2 by 15 to get, well, basically be 3 ounces. 3 of the 15 ounces is in copper. Now, what they're doing is saying 3 out of the 15 there, but let's add more substance without adding more copper. That more substance is more silver, pure silver. We have to find out how much pure silver to add. So they're saying, let's turn this, and they're saying 7.5%. They're saying, let's turn something that was 20% copper into 7.5% copper by adding more of this thing. What I was going to do was very similar, but I was only going to do it in terms of silver. I was going to say, if you take the 80% of silver times 15, 80% of the 15 ounce thing is silver, and you add this many more this many more ounces of pure silver, and divide it by 15 plus the amount of pure silver here, then you want it to become 9.25, excuse me, 0.925, which is 92.5%. If I solve for x this way, I should get the same thing. I do a lot of this stuff when I'm showing students how much you need like on your final exam or something like that to get a certain grade. This is the kind of thing that I do. So it's something I'm very familiar with. They're doing the same thing here. They cross multiply. 100 times 3 is 300, and they cross multiply over there, and then they solve. They get x equals 25, which I guess that means you need to add 25 more ounces of pure silver for this to work. So in this one here, let me try it on this one and see if it works. 80% of 15 is 12. So we're doing 12 plus x over 15 plus x. And no, you cannot cancel anything out or reduce anything there. If I multiply this upward, this 15 plus x, though, then I would distribute there. I guess this is going to take more work, so I guess I can see why they're doing it, because this has multiple x's. Give me a moment. 0.925 times 15. And I'm getting 800. Oh, what did I do? 0.925. Sorry about this. 0.925 times 15. All right, 13.875 plus 0.925x. I'm just showing you an alternative way to do this. It's an either or case. What they did was fine. 0.075x, if you subtract, equals, and that's 1.875, and you divide both sides by 0.75, minus 12 and divided by 0.075, and you get 25. So I get x equals 25 this way. Same answer as they got before. So you should mix 25 ounces of pure silver with the 15 ounces of 800 grade silver. So you have two different options on how to do it. They're doing it based off the proportion set. I'm fine with it. I'll follow that if the problems are like that. Solving by using the least common denominator. Okay, so this is what we're trying to build toward here. When a rational equation is not expressed as a proportion, you can solve it by multiplying each side of the equation by the least common denominator of the rational expressions. Give me a second. I would argue, okay, I was trying to see, because the last section, it was either last section or 2 sections ago where they said, here's method number 1, here's method number 2. I would argue these problems have 3 different methods to solve. And this one is probably the way I personally can find myself doing it. Method number 2 is just like okay, there are 3 methods. The first method I want to state is before these. They said when it's not expressed as a proportion, method number 1, make it a proportion. So method number 1 is take this thing, make these into one fraction, get a common denominator by these, and boom, this over this. So listen, this isn't even a version that they do. So I just want to show you a different version really fast. If I multiply this by 4 over 4 and this by x over x, you get 20 plus 7x all divided by 4x equals negative 9 over x. Boom, I made it a proportion. Now you could cross multiply. That's a method. I don't generally plan on doing that. I don't know if I ever, for the most part, do plan on doing it. But that's a method. You can make it a proportion by making a single fraction on one side. That's one version. Now, another version is what they're doing. The other 2 versions is what they're doing. But what they do with it, people might get a little confused by, specifically the distribution right here. We are seeking the least common denominator of these. The least common denominator of x and 4 is indeed 4x, but they don't ever write the 4x down on bottom. They just say if we multiply everything by 4x, then surely that 4 and that x will somewhere divide with your terms and make this thing clean up. So 4x times 5 is 20x. Well, why doesn't this say 20x? Because it divided by x and those x's are gone. And then here, 4x multiplies with 7. Why doesn't this say 28x? Because 28x divided by 4 is 7x, and that's why the thing is gone. And then 4, and same thing here, the x's go away, and you get negative 36. So the third version that I sometimes do, and I'll probably show a couple times before I do this distribution bit probably, is that I would get a common denominator, multiply this by 4 over 4, x over x, and 4 over 4, and then you get, did I say 4 over 4? 20 over 4x plus 7x over 4x equals negative 36. 6x over, negative 36 over 4x, that you first get the common denominator, and then you clear these out. Once these all divide by the same thing, now you can multiply by 4x, and then boom, you get this equation here. Sorry that I'm slowing down on this. I just want to talk about all the different versions of how this may be written, especially when I write it. Who knows what's going to happen. Anyway, you solve for x, you get x is negative 8. The only x that would have been a problem was x equals 0, and that's not what the x is here, so we're all good. Part B, yeah, I might go more toward common denominator things, because you have to first recognize what you need as your denominator, or what all the different multiples of things are. Like this needs to multiply by x over x, this needs to multiply by x minus 5 over x minus 5, and this needs to multiply by both of them. But the idea is the denominators will go away, and I get it. I'm good with that. You can ignore the denominators if you'd like to. Just understand what this means when you distribute these values, because people have a lot of trouble with this part. When I distribute x times x minus 5 into both of these, you might go, wait a second, where did the x minus 5 go? Well, it divided with this x minus 5. And wait, where did this x go right here? Well, it divided with this x. So those are the parts you might miss. This becomes a quadratic, so a reminder on how to solve quadratics, especially by factoring. You can set everything equal to 0, and then factor and use zero product property to solve. You get 1 or 15. Now, both of these seem to work as well, and if you check the original equation, you can see the x's that wouldn't work would have been 5 and 0. So 1 and 15 are fine. So again, I'm not going to double check by plugging numbers in like this. I'm only going to see if I had extraneous solutions to begin with and then count them out. Now the next page I think mentioned, yes it does. When solving a rational equation, you may obtain solutions that are extraneous. Be sure to check for extraneous solutions. Now we did extraneous solutions back with at least logarithms. I don't remember where else, but we did them with at least logarithms. We couldn't take log of negative numbers. I did them in IM1 with absolute value equations as well. So there are a couple places to do that. Why do rational equations have extraneous solutions, possibly? Because what before was fraction form, dividing by potentially 0, eventually you bust the fraction. So eventually when the fractions are gone, something that you might have been dividing by 0 with is, something you just got to be careful with. That's basically it. So let's look at the extraneous solutions here. X can't equal negative 3 or positive 3, right? Straight up, these are two answers that x are not allowed to be. So if we get either of those solutions, which we likely will based on this example, we'll take care of that. So they factor this x squared minus 9 to x plus 3 times x minus 3. You see what's missing in these. This is missing in x plus 3. That's probably how I'm going to do most of these. This is missing in x minus 3, and then get rid of the bottom, basically. That's why we're multiplying everything by that. That's the actual math. So 6 times that and negative 4x times that. And then you deal with a quadratic and you solve by factoring. They're going to factor again and they get these two numbers. Now, negative 3 is one of the extraneous solutions here. So this won't work. You notice that, boom, it's a restriction in our domain. You can see division by 0 is undefined. Substituting negative 3 is a problem. Substituting 3 halves is good, which I won't bother checking, but there you have it. You can also graph each side of the equation and find an x value where the graphs intersect. And you can see it only intersects at 1.5. Only at 1.5. It doesn't intersect at negative 3 for x over there. Okay, so only at 1.5 is 3 over 2. And the apparent solution, negative 3, is extraneous. Okay. Find the inverse of a rational function. So finding an inverse is swapping x and y and solving for y all over again. So we have this one here. It says determine whether the inverse of f is a function and then find the inverse. They are graphing to determine it. I think I'm just going to solve it and then tell you one way or the other. Their graph is, does it pass the horizontal line test? And this does, because, listen, that's an asymptote right there, but no horizontal line passes through more than one x value for some y value. So we're good there. Swap x and y to take the inverse and then solve for y all over again. They multiply both sides by y plus 3 and divide both sides by x. You're going to see this quite, we might have done this before, I can't remember, but you're going to see this action quite a bit when we hit our trigonometry units. I think we have a couple chapters on trig. You're going to see me switch places of these things a lot. Boom, boom, there they go. But it's multiplication of y plus 3, division of x. Without needing to distribute the x, right? And then you can subtract 3 from both sides. Boom, you get this by itself, and there's the inverse. The inverse is indeed a function. How can me solving the... I said I might solve it first to determine whether it has an inverse or not, whether the inverse is a function. How can I use my equation to determine that? The ones that won't have inverses will probably have some sort of plus or minus involved, which means plugging in some x can get me more than one y, And that's just not the case here. I can only get one possible y from this one by plugging in any x. I can't plug in 0, but that's not the point. The point is, am I getting multiple y's for the same x ever? The answer is no. So how will I ever get those situations? If you have like something squared and you got to take the square root of both sides, you'll get a plus or minus, something like that. Solving a real life problem, I'm sure this has to do with inverses. In section 6.2, example 5, we wrote this function. Oh, that was an average of something. Average cost of making M models using a 3D printer. Find out how many models must be printed for the average cost to fall to $90, and by solving an equation and using the inverse of the function. There are two different ways to do it. One is substitute 90 right now and solve for M. It looks like that's what they're doing in this version here. And what they do is they multiply both sides by M to bust the fraction, subtract 50M, and divide by 40. Alternatively, you can get M by itself. They do something different than I would have done. What they're doing is fine. So they split this up. They have, basically, this would have been 50M over M, and then those M's are, gone here. So you're just left with the 50. Remember, you're not swapping M and C, but you are getting M by itself. If I subtract 50 and then multiply both sides by M, divide both sides by C minus 50, you get that equation there, and that's fine. And then you can substitute 90 straight into that one. 90 minus 50 is 40. 1,000 over 40 is 25. You get the same answer. What I would have done, I don't know if this will look bizarre to you. I would have done basically the same thing the first one's doing, only without the 90 there. You might wonder how this thing works. If I multiply both sides by M to begin with, I'll just do C times M, I guess. Then I have C times M equals 50M plus 1,000. And I can get M's on one side of the equation like this. You might say, what do I do with this to solve for M? You factor M out. It's a common factor. And then I can divide both sides by C minus 50, and I get M is 1,000 over C minus 50. I get the same answer there. That's how I do those more often. I guess either works. Theirs is fine through that division. So I guess we got to look at both. It depends on what we do there. 25 models are printed. Boom. So we can solve for it that way. Okay, that's the end of the lecture portion, guys. Let's go to the vocabulary and core concept check. Number 1, when can you solve a rational equation by cross-multiplying? Explain. They stated when you have one term, one rational expression on each side of the equation. I can just state when it's a proportion. When you have a proportion of one rational expression, one rational term equal to another. I guess that's my explanation as well. Number 2 on writing, a student solves the equation 4 over x minus 3 equals x over x minus 3 and obtains the solutions 3 and 4. Are either of these extraneous solutions? Explain. X equals 3 would be an extraneous solution because if I substitute 3 into this equation, I get 3 minus 3 in either denominator and that becomes 0. I'm not allowed to divide by 0. X equals 3 is an extraneous solution because it leads to a 0 in the denominator, in each denominator, and division by 0 is undefined. Okay. All right, those are our 2 things we got to look out for. I'm going to go ahead and get started. Let's take a look at numbers 3 through 58. There's yet another 58 to do, and this is the last section in the chapter. Get myself set up here. I have to change slides and do things like that. Get my pen ready. Okay, that is the right pen. Let's go ahead and get started. In exercises 3 through 10, solve the equation by cross-multiplying. Check your solutions. I always thought cross-multiplying was hyphenated. I was going to say that earlier on, but now it's really sticking out to me. I ignored it, and it came back. So they told us to cross-multiply, so cross-multiply I shall do. Multiply both sides by 2x, multiply both sides by x plus 6. Ultimately, the fractions bust, and this is what it's going to look like. 4 times that equals 5 times that, and that's how cross-multiplying works. Do not do cross-multiplying in instances where it does not belong. Guys, I'm going to do this algebra really fast. There's no need for me to stick around with this kind of algebra. So I got x equals 4. 0 and negative 6 would have been extraneous solutions, and that is not either of my answers. I don't expect to actually get extraneous solution answers until they kind of bring them up. So I'll remind you of what x isn't allowed to be, and as long as it's not that, we're good to go. Number 4. We cross multiply again. X plus 2 multiplies with 9, and 4 multiplies with 3x. Now, there are other ways. Listen, I saw this for this one as well. 4 over 2 could have reduced to 2. 9 over 3 can reduce to 3. There are things you can do before cross multiplication if you truly want to solve it that way. If I see another one to reduce, I don't see another one to reduce, so I probably want to do it on this one in just a moment, just to kind of show that hey, it's the same thing. Obviously, I think you should know it's the same thing, but if you can make numbers smaller, I would sometimes bother with doing it. Here I'm getting x equals 6, which is neither 0 nor negative 2, so you're good. Alternatively, like I said, 9 over 3 is 3, so this could be rewritten as 3 over x equals 4 over x plus 2, and then when you cross multiply there, you get that. So 3x plus 6 equals 4x, and now x equals 6. I don't know if that's less steps or not because I didn't have to copy down the problem again, but you still get x equals 6 regardless. Number 5. Whoa, what are we doing? Number 5. I have this guy. Now, I'm going to mention it now as we're doing these problems through cross multiplication. Cross multiplication is only allowed with proportions, a single fraction on either side of this thing. Otherwise, you cross multiplying wrong. You're misunderstanding the idea of cross multiplication and what we're truly doing with the problems. That being said, you can, well, you can't see them, but there are going to be problems later on where we do not have proportions. And just like the lecture portion, we have ways of solving them that we learned on methods. And I introduced a version of a method that says if you make them fractions like these are, then you can do cross multiplication. And I intend on probably doing it at least once for a problem, if not at least making it an alternative version of a problem. We'll see. Anyway, cross multiply again. 8 multiplies with x minus 1. 2 multiplies with 3x minus 2. Now, I'm going to try something different here. I can divide these both by 2. Boom. Right? Just getting rid of the 2 there and the 2 there. Just, saving a little bit of time. Distribute the 4. Subtract 3x, add 4, you get x equals 2. So there's number 6. 1 and 2/3 would have been invalid solutions, though. Number 7. All the rest of these look like they have quadratics involved. You might say, hey, I don't see any x squareds here. We haven't cross multiplied yet. Here we're going to multiply an x with an x. X minus 1 will multiply with x, and boom, a quadratic is born. And 2x plus 7 with x minus 5. So through distribution, you get x squared minus x. Through FOIL, you get 2x squared minus 3x minus 35. Let's set this all equal to 0 by subtracting x squared and adding x. And this is factorable. This factors into x minus 7 times x plus 5. Therefore, x equals 7 and negative 5. 7 and negative 5 are fine. 1 and negative 7 halves would not have been fine. Again, I don't expect extraneous solutions with these ones, but you never know. You never know. Number 8. When I cross multiply here, negative 2 will distribute an x plus 1. And here we got to FOIL x minus 8 with x minus 1. This is x squared minus 9x plus 8. Set it all equal to 0. I'm going to add 2x over and I get negative 7x. I add 2 over and I get 10. And this is factorable to x minus 5 times x minus 2. Outside of the cross multiplication step, which I don't know if that's truly new for any of you guys watching. Maybe it is, maybe it's not. But outside of the cross multiplication step, none of the other stuff's new. Solving quadratics, things like that. And because none of these have extraneous solutions, I would also truly say that these are, I mentioned it before, we were around probably number 5 or number 6, but you can turn any of the other equations we do into proportions if you'd like to. The problem is when people start seeing these as different kinds of questions. I get it. We can cross multiply. I do. But these are not different kinds of questions. We are solving rational equations. We just multiply in such a way that it magically just so happens that this multiplies with that and this multiplies with that. That's the kind way of working this out. 2x squared minus 6 is x squared minus x minus 6. Subtract x squared over, add x over, add 6 over, Ooh, I got a common factor of x where I have x plus 1 here. A lot of people would look at this and go, what do I do? Factor out x. It's a common factor. But using zero product property, x can equal 0 or negative 1. Negative 2 is an answer that would not have worked, but 0 and negative 1 are fine. And then number 10. So I like these problems. I could do this 58 times. I'd run out of things to say. I already have run out of things to say. You can tell that I'm rambling about other things while doing these problems. Hope that's okay. X squared minus 27 is not a difference of two squares. It doesn't matter. We're not trying to factor anyway. We cross multiply. Negative 1 times x squared minus 27 is negative x squared plus 27. If I FOIL these two right now, boom with boom, you get x squared. I'm saving myself a step. X squared minus 7x plus 12. Save steps where you can. If I add x squared to both sides, I get 2x squared. If I subtract 27 from both sides, I get negative 15. Let's see if this is factorable. I assume it is. 3, 5, 3, 5. Negative 5, wait. Negative 5 and positive 3. That's negative 10 plus 3 is negative 7. So there we go. So this x is 5. This x here, subtract 3. You set it equal to 0, right? This plus this equals 0. Subtract 3 divided by 2. You get x equals negative 3 halves. 3 would have been an issue. The square root of 27 plus or minus square root of 27 would have been an issue. These are neither of those numbers. Okay, number 11. So far in your volleyball practice, you have put into play 37 of the 44 serves you have attempted. Solve the equation 90 over 100 equals 37 plus x over 44 plus x to find the number of consecutive serves you need to put in play in order to raise your serve percentage to 90%. Okay, now if you followed along with what we did in the lecture portion, this is very similar to a problem that we had. It actually rings a little more true to the way that I set it up, because I did it in an alternative way, which is you need to do this many more, serves? You've put into play. How many more serves you put into play? So you need to put this many more serves into play, and this is number of attempts that you have here. It's equal. It needs to be a consecutive amount. We need to add this number. We have to be a 20 for 20, whatever it is, a perfect 20 out of 20 to get 90%. That's what we're trying to do here. Now, they set it up in such a way that we can cross multiply. So I'm not going to do anything other than that. We'll just do that. I'll reduce this to 9 over 10 before I begin, though. And no, there's nothing I can do on the right side of this equation as far as reduction. No canceling, no nothing. So we will cross multiply. I'll do 9 times 44 plus x equals 10 times 37 plus x. And I fully intend on fronting with my x's. 9 times x and 9 times 44. 396. Yeah. Equals 10x plus 370. Subtract 9x from both sides. Subtract 370 from both sides. You get 26. 26 more serves. You have to do a perfect 26 of 26 of returns in order to build up to 90%, given the amount that you have. We have 37 of 44. We're currently at 84%. It just goes to show what kinds of things you need. It's like this. You got 37 out of 44 points on this test. Your next test is out of 26 points. You need a perfect 26 out of 26 to now go from 84% to 90%. It's, you know, excellence requires high high success rates. Number 12. It's crazy how much that does that, and yet if you don't return serves, how fast it lowers, really. Number 12. So far this baseball season, you have hit 12. You have 12 hits out of 60 times at bat. That is a 200 average. Solve the equation. Oh, you need a 360 average? Okay. Solve the equation. 0.360 equals 12 plus x over 60 plus x. At least it's your early on in this season. To find the number of consecutive hits, you need to raise your batting average to 360. Be like Ichiro or Barry Bonds in the 04 season. Not that I want to call it cross multiplication here unless you put this over 1. You can, but 1 times that is just that number. I got to multiply both sides by 60 plus x, given the way that it's written. You could turn this to 36 over 100, but I think at this stage we'll just leave it like that. So 60 plus x on both sides multiplying. So here, you will have 36% of 360. I know that number. Wait. 36. I'm having trouble with this. 6/10. Oh. I'm having trouble. I don't know why I'm having trouble with that. It's not 6/10. 20. Oh, no, it's not a clean number. 21.6. 21.6 plus 0.36x equals 12 plus x. If I subtract 0.36 from both sides, I get 0.64. And here I get 9.6. And I divide both sides by 0.64, you get x equals 15. 15? Really? I thought that would have been a lot. Well, I guess that you're really early in the season. So 15 more hits. Now, 15 out of 15, given that you've been hitting 200, is quite far-fetched for you to get. But 15 consecutive hits gets you there. You'd be then 27 for 75. And 27 out of 75 must be a 360 average. Look, I guess 36% of your hits still sounds really low. And mathematically, I guess it's achievable by going a 15 for 15. I guess that makes sense. But it just shows how hard baseball is with respect to that. You ain't going to do that. No one's going to do that. You just won't be lucky enough. It's not even about being skilled. You just won't be lucky enough to do it. Number 13, modeling with mathematics. Brass is an alloy composed of 55% copper and 45% zinc by weight. You have 25 ounces of copper. How many ounces of zinc do you need to make brass? So is the copper pure, I suppose? So we have pure copper here. We need 50. We have 25 ounces of copper. Do you need to make brass? I'm overthinking this problem because I want to write it like the other ones, but I feel like I don't actually need to. If I make 25 out of how much I need in total to become 55%, no. Let me think about this with respect to the other kinds of problems that we had, because this is pure copper. So let me think about that. Okay, so there's nothing inherently wrong with what I'm doing. I mean, X isn't the solution. I need to think about what I'd have to write as a whole to solve this in a way that would look like the other problems. For now, I'm just going to leave it like this, because what this X represents, and I'm sure there's another way I could be writing this that's significantly better. I apologize for not doing it earlier on. I want to turn 25 here into 55%, means I need to add a whole total to this here. If I, swap these things, I get X is 25 over 0.55. See, the problem here is I'm going to answer the question, but it's not going to necessarily be to the liking. Hopefully it's to a liking of understanding, but this is 45. This is an approximation, by the way. It's look at this calculation. We're getting 45.454545, etc. So we're getting about 45.5, I'll say, around 45.5 ounces total. So if I have 45.5 total ounces of brass, 45.5 minus 25 will end up being this answer, which is 20.5 ounces of zinc. That's how much is needed. That being said, what I could have done, I don't know. I'm just going to leave it like that. That is the answer there. That gets you 55% of one and 45% of the other. You just need a certain total to make that happen. Okay. Anyway. Number 14. You have 0.2 liters of an acid solution whose acid concentration is 16 moles per liter. Ooh, they have a whole formula for us right here. You want to dilute the solution with water so that its acid concentration is only 12 moles per liter. Use the given model to determine how many liters of water you should add to the solution. You have 0.2 liters of an acid solution whose acid concentration is 16 moles per liter. Concentration of original solution, volume of original solution. So our new solution, I'll just put X there for now, I don't really know. Concentration times 16 moles per liter times 0.2 liters is that number of moles. You want to dilute the solution with water so that its acid concentration is only 12 moles per liter. So we want this to be 12. And we want to divide this by the volume of the original solution plus the volume of water added. So that's going to be our setup. I mean, all this makes sense when I look at it. 20%, well, I don't know if this works as percentages, so I'm not going to say that. Never mind. That's because that's not a percentage. That's a liter amount. I got to think about how the 16 works, but we got to reduce the moles per liter on that thing. Okay, so I'm going to multiply both sides by 0.2 times x, and here you'll have 12 times 0.2 plus x, 0.2 plus x equals, and 16 times 0.2 is 3.2. So 12 times 0.2 is 2.4. If I subtract 2.4 from both sides, you get 0.8, and divide both sides by 12. That's a repeated decimal, right? It's like 230. Wait, is that 1/15th? Let me figure out what this is. 0.8 divided by 12. It's 0.6 repeating. 0.06 repeating, excuse me. I believe that's 2/30ths or 1/15th. If I go to the calculator here. Yeah, 1/15th. So 1/15th of a liter, I guess, but just 0.6 repeating, I guess is what we can say for x. 0.16 liters of water. All right. Okay, numbers 15 to 18. Identify the least common denominator of the rational expressions in the equation. For all of these, there's really no work I got to show for the majority of these. I don't even see anything I do got to show per se. Just find what's missing in the other things and say what you have total. We did this in the past. We just only had these numbers. What's the least common multiple of x and x plus 3? Well, it's x times x plus 3. Like that. That is going to be the least common denominator of those two together. This is what we need to find as the common denominator for all three of those. So this kind of works out the same way we did addition and subtraction. We're just not solving anything or simplifying anything right now. You're just saying what this thing needs as a whole. Number 16. So I'm not even looking at the numerators. I'm just looking to see if there's something to factor in the denominators, and so far, nothing. X times x minus 1 is what we would want right here. I guess this is a good way of talking about these so that in the future problems we know what we're seeking for least common denominators. It'll make a whole lot more sense when we do those problems. So then we can do them in kind of the way that the book's talking about them. In this case here, 2 times x plus 4 times x plus 1 would be the thing, right? We would need all three of those for a least common multiple. There ain't much to do on these problems other than kind of provide these answers. Number 18, because there's nothing to factor. And nothing is shared. There's nothing shared among these common denominators, so except for ones that are identical. But it's not like we got to factor and see what's the same and see what's different. I'm sure in future problems we will have some of those. 3's got to multiply. All of these got to multiply. 3 times 2x minus 1 times x plus 9. So I guess they're just getting you prepped for that kind of business. Okay, those are the 4 different answers there. Okay. Numbers 19 to 30, this is where, we have to do the majority of our work here. Solve the equation by using the least common denominator and check your solutions. Now, checking your solutions means there are probably extraneous solutions to be had, so be prepared for them. I will. Excuse me. 3 halves plus 1 over x equals 2. Okay, there's more than one way to solve these problems. I've kind of mentioned that several times. There's the way that we're kind of looking at right now, which is straight up finding out the least common denominator of these three. The least common denominator of these three is 2 times x. So if we multiply all of these things with 2x, we do 3 halves plus 1 over x equals 2, and multiply all of these things here by 3x. 2x, excuse me, by 2x. Then distributing 2x into here, 2x times 3 is 6x over 2 is 3x. The bottom line is the 2's would cancel in that, but I can't write cancellation because the 2's got to multiply over here. This is where it can get a little confusing looking. 2x times 1 is 2x over x is 2. But again, the x's would cancel there, but you dare not write the actual cancellation, you just divide them. And 2 times 2x is 4x. So there's a cleanup of what we have there. Now, before I move on to solving this problem, which actually it's really fast, let's subtract 3x, you get x equals 2. So in solving that problem, we get x equals 2. That's one version. Another version is getting that least common denominator of 2x, and this might look a little slower for you guys here, but we'd multiply this top and bottom by x, this top and bottom by 2, and this top and bottom by 2x. Now you have, clearly you can tell this is 3x, and this is 2, and this is 4x, but they're all dividing by 2x. The thing is, though, them 2x's don't matter anymore. They're all the same denominator. As long as you're all dividing by the same thing, then you can just write this. This is probably how I generally like to write the majority of these and just say what's missing in them and multiply them. I only truly need to multiply the top, though, because the bottom can go away, but that's only if you understand why they go away. So every one of these have an as long as you understand kind of setup. The third option is this. Create a proportion out of it. So creating a proportion out of this, multiply this by x over x, this by 2 over 2, and now you have 3x plus 2 all over 2x. Keep this one the same as 2, whatever. And now you have a proportion. Whether you put 2 or 2 over 1, you can cross multiply because it's a single fraction. And if you do, notice how 2 multiplies with 2x, and you get, once again, the 4x that's there. So you have multiple different options to do it. I might have different perceived appearances of what I'm doing, and I apologize if they look a little strange here and there, but I think it might help more than doing this part here, so you might be confused on what divides or why we're multiplying by those. So here, and by the way, this will help us more for when we talk about common denominators as a whole in expressions. So for this one, for example, this guy, these need to multiply by 2 here to match the 6, and this needs to multiply by x here. Now, the bottom line is, literally, no pun intended, bottom line is these all have 6x on the bottom now. Do I need to write the 6x's anymore? Not really. I'll write it just this one moment right here. And no, you're not trying to cancel anything right here. You actually want this to be written this way. Because now when you multiply everything by 6x, which is technically what the book does with this, 6x cancels out, right? So we have 4 plus x equals 8, and subtract 4, you get x equals 4. By the way, I didn't mention on the previous problem, I did see it, but I didn't mention, x equals 2 works because the only value that wouldn't have worked was 0. X equals 4 works because the only value that wouldn't work here would be 0. So those two work. Those are not extraneous in any sort of way. Number 21. We have x minus 3 over x minus 4 plus 4. I'll just put it over 1. I think it's to your benefit to do that each time. Equals 3x over x. That's weird that it says, well, listen, I'm going to solve this in a way that I choose to solve this, okay? You know what? Forget the 4 over 1 for a moment. You know what 3x over x is? It's 3. Now, that being said, you got to remember that x can't equal 0 in your final solution. X also can't equal 4. So let's see if we get either of those solutions. But if we cross those out, now we have x minus 3 over x minus 4 plus 4 equals 3. And I can subtract 4 from both sides and get negative 1. Now I have not a proportion, but I can multiply both sides by x minus 4. And I get x minus 3 is negative 1 times x minus 4, or negative x plus 4. Add 2x to both sides, add 3 to both sides, divide both sides by 2, you get x equals 7 halves, which is neither 0 nor 4, so we're good there. Kind of an interesting question since they had things that could reduce by x's. X's could eliminate. You know what I think actually would have happened here? And maybe I shouldn't have, I did it, but I shouldn't have done it, is that I bet if I solved conventionally, you would have gotten x equals 0 as a solution, and we would have rendered 0 as extraneous. I'll save that for another problem because this one was very set up for me to just kind of cancel those things out. I'm fine with canceling that out because 0 is not allowed as a solution. You can't cancel them out in other situations where it is, but that one's not allowed. So we'll do that in another problem. Speaking of which, other ways to solve these problems are as follows, and this is a little rambunctious for me to do these a lot of different ways, but I want to show you a lot of different ways. You can solve it however you'd like. These both share x minus 3, therefore they have a common denominator, which means if I subtracted 2 over x minus 3 on this side of the equation like this, I can just combine that top Now I have 1 over x is x minus 3 all over x minus 3. And those don't cancel, by the way, but x minus 3 over x minus 3 is 1. Boom. 1 over x equals 1, you get x equals 1. Boom, like that. This is yet another example. Maybe I'm misrepresenting these problems. What I'm writing is correct, but maybe I'm misrepresenting the nature of these problems and how they should be approached. And I apologize for that. This is my nature of sight reading and saying you can do problems the way that you want to do these problems, right? It's kind of up to you. Do these problems the way that you'd like to. Try to see if any of these other ones get tricky like that. Maybe, maybe not. Anyway, x equals 1. Listen, did I, in effect, cancel out a solution of x equals 3 by dividing these and making them 1? Yes. But is x allowed to be 3? No. X isn't allowed to be 0 or 3. So if x equals 3 is a solution that you get, it's extraneous. So I'm actually removing the idea of even checking for extraneity while doing these problems. Can I do that for every problem? No. I want to show you different versions of ways to do them. You're probably like, you're messing with my head, Mr. Robinson. What are you doing? The math is mathing. That's what I'm doing here. Here's what I'd prefer you do. Consider my strategies or do it another method and see that you get the same answer. Right? Maybe you just want to know what the answer is and you're seeking alternate ways. So I want to give you the different ways. This is a problem where I'm not going to, nothing up my sleeve. I'm not doing anything fancy. I'm going to find a common denominator with all these. This needs an x plus 4. This needs both x plus 4 and x minus 1. Now x plus 4 times x minus 1 is x squared plus 3x minus 4. I didn't used to do this, but I really should because it's easier to distribute the 4 after. And this needs the x minus 1. Now that they all have a common denominator, I'm going to ignore the denominator. I hope that's okay by me doing that. I'm kind of showing why we can do that. But be careful what's extraneous, right? Negative 4 and 1 would be extraneous. All right, let's distribute. 6x squared minus 6x plus 4x squared plus 12x minus 16 equals, now we got to distribute these two, right? This is our FOIL. 2x squared plus 8x plus 2x plus 8. Plus 8x plus 2x plus 8. All right, here's our setup, and let's solve. Hold on, let me check a text really fast. It's one of my assistant softball coaches. They're looking at purchasing a batter's box mat, and I said go for it. Okay, 6x squared plus 4x squared is 10x squared. Negative 6x plus 12x is 6x, and we got a minus 16. And before I do anything more with this, everything here can divide by 2. So I'm going to do that. I don't want to deal with bigger numbers if I don't have to. I could have divided by 2 to begin with. I just realized that, but that would have been a little too fancy for some people. They would have said, wait, what are you doing? All right, subtract x squared, subtract 5x, subtract 4. And this factors into, does that factor? X, hold on, I want to make sure I didn't make a mistake there. Oh, 5x squared, I'm sorry, 5x squared minus x, this is 4x squared. Oh, I can divide by 2 again. Oh well. X squared, 2x squared minus x minus 6 equals 0. Okay. I was like, what's going on here? All right. Negative 4 plus 3 is negative 1. Okay. So this solves in 2x equals negative 3. X is negative 3 halves. Is that worth it? Looks like they cost $300 to $400. Maybe it's cheap. Sorry. Let me respond to this text one more time. Okay, apologize if I do pauses here and there. These need pretty immediate responses from me. Okay, x equals negative 3 halves and x equals 2 would be the two solutions there. Now, is that negative 4 or 1? No. So are they extraneous? No. So those are our answers. I did dividing by 2 twice. Maybe I should have put it on one side of the equation before dividing by 2, I suppose. I'll ask about it. Okay. All right, number 24. We have 10 over x plus 3 over 1 equals x plus 9 over x minus 4. If we're going for here, I'm gonna do a proportion one again. Hope you don't mind. I just want to bring one back again. So putting these all over x, you get 10 plus 3x all over x equals x plus 9 over x minus 4. I didn't change any of the denominator action, with regard, I didn't cancel anything out, but now we can cross multiply from here. So just keep in mind, you're allowed to do this kind of stuff. 3x plus 10 multiplies with x minus 4, and x multiplies with x plus 9. Is this faster, slower? For this problem, it might be faster, because otherwise I have to multiply by x and x minus 4, and yeah, we'll just get there. 3x squared minus 12x plus 10x minus 40 equals x squared plus 9x. Subtract the x squared, subtract the 9x. And 8 minus 8 and plus 5. Negative 16 plus 5. Boom. So that equals 0. So x equals negative 5 halves and x equals 8. The non-solution, the domain restrictions would have been 0 and 4, and this is neither of those ones. Okay, number 25. 18 over, I'm going to do this right now, guys. I'm going to factor x times x minus 3. I think on these problems I will immediately factor just to get them set. Notice it did say x squared minus 3x, but my goal is find what's missing in these other guys here. So this needs to multiply by x. This needs to multiply by x minus 3, and then we have a common denominator. Now that we have a common denominator, I will ignore the denominator. So I'm doing what the book is doing. I'm just giving it a different appearance. By my ignoring the denominator, that is multiplying both sides by x times x minus 3, and therefore rendering them useless. However, we do have to distribute, we do have to mind ourselves of the 0 and the 3 as possible extraneous solutions. If I add 6x to both sides and add 15 to both sides and divide both sides by 11, I get x equals 3. X equals 3 is an example of an extraneous solution. That's actually not allowed. So because that's extraneous, there's no other solution to offer. This is no solution. So if that's extraneous and there's nothing else there, that's what we have to put. We have nothing else. Boosters is not really giving us a budget until parents pay the booster. Okay, number 26. $10 over, and I'm going to factor out an x here. I get x times x minus 2 plus 4 over x equals 5 over x minus 2. Let's get that common denominator. Multiply x minus 2 on these two. Multiply x on these two. The denominator is common. The denominator goes away. This is only for equations. I never did this for expressions. We are multiplying both sides by x times x minus 2. That's what makes it go away. 4 distributes, we got 5 times x. I subtract 4x to both sides, get x, and 10 minus 8 is 2. We get x equals 2, and yet 2 is not allowed. This is the section of no solutions, 25 and 26. The odd and even together. This special cases, if you will. Okay. Number 27. 27 is one of those ones, if I wanted to, I could, and maybe it's overkill, so I won't do it. Maybe I'll show both, and you can decide which one you prefer. Okay, let's do it the old-fashioned way. Let's find common denominator. This needs a couple x's. This needs a couple x plus 6's. This needs a couple x's, like so. Okay. Now the denominators be gone. I got x squared plus 1x plus 1x plus 6 equals 2x squared plus 1x. X squared plus 2x plus 6 over here. I'm going to subtract these guys over here. I get x squared minus x minus 6 equals 0. And this factors 2x minus 3x plus 2. So x equals 3 and negative 2, which are allowed as far as answers go. Alternatively, with this problem, I could have. Alternatively, with this problem, I could have done what I did once before and said, and this isn't a common thing for me to do, but seeing the x plus 6 as a common denominator, I could have subtracted this x plus 1 on this side, distributing the negative, of course. So let me just write it all as one fraction. This is all over x plus 6, so subtracting the x plus 1 looks like that, you know, so it's gone over here. And now I have 1 over x equals 2x minus x is x, 1 minus 1 is 0, so x over x plus 6. Boom, look at that. Now I have x squared equals x plus 6, x squared minus x minus 6 equals 0, and you get the gist. We're back to where we were up there. So whichever way you prefer to solve, that actually looks like less work. It just depends on what you want to do with it whenever they both share something like that. I think number 28 really does call attention to doing that. So again, I'm going to do it when it calls attention to itself to say, hey, you might want to try it. And I think this is one of those times. So this one here, notice that once again, I got x minus 5s on both denominators, on the denominator here and here. So if I subtract this x over here with that common denominator, x minus x is 0, and I'm just left with 5 on top. This lets me have a proportion where I can cross multiply. And I bring this stuff up. This isn't going too fancy. This is a method that works. This gives us credence to why we had a whole section devoted to cross multiplying, because we can use the cross multiplying whenever we have proportions. We can make proportions whenever we can make single fractions. And I do think that this is a valid thing to talk about. Do I do this all the time? Not necessarily, but I don't do things the same way that you're seeing right here. I do a lot more mental math in my head. I do a lot more scribbly work. This, by the way, I subtracted 5x over. I'm adding 15 over, and then that's gone. I do a lot of work in my head. I'll say that. Like personally, if I did this on the side. So x equals 0, x equals 7. Now let's see if those are extraneous solutions. They're not. Only 5 and 3 would have been extraneous solutions. So those two are good. Anyway, I just want to keep those in mind for you, that I'm not always doing things the way that I would do them as far as full work shows. I'm giving you different versions of them. I don't mind what I just wrote at all. That was actually very fine. That seemed like a decent problem to do it with. This one, it depends on what you want to do. If you want to get a common denominator with x's, you can. If you want to, just on the left side, to make a proportion. If you'd like to instead do the whole get some x's here, get the x and x plus 3 here, and get the x plus 0 x plus 3 here. You can see that this seems like it's just more work as an overall. Common denominator, distribute the 5, distribute the 2. This is a minus this time. So we're doing minus 2x. This is x squared plus 3x, right? So minus 2x squared minus 6x equals 2x. Let's clean up this side first. All right, let's add the 2x squared over. Let's add the x over. Let's subtract the 15 over. I don't think this is factorable. I don't think it's factorable. I'm going to use quadratic formula to solve this one. I'm going to start with the discriminant. Again, something I actually don't do myself, but I think it is easier. Because I do a lot of mental math. That's why. So b squared minus 4ac is 9 plus 8 times 15, 120, which is 129. Yeah, this was not factorable, assuming everything I did is correct before that. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So these are the two different solutions we're going to have. These are exact ones. I don't see a need to approximate. They don't mention any approximation of any sort in terms of rounding. And those are clearly not going to be 0 or negative 3 because there are not rational solutions for this set. So I think we're good there. Okay, number 30, last one of this set. And we're only halfway through all the problems, so probably a lot more to do of different kinds. Oh, let me factor that. This factors to x plus 3 times x minus 2. And this equals 2 over 1 plus x minus 3 over x minus 2. All right. This guy's missing both parts. X plus 3, x minus 2. That does multiply, remember, to x squared plus x minus 6. So I'll do that on top. This needs the x plus 3 right there. That's a difference of 2 squares when multiplying that set. Now I have a common denominator. So I got 5 equals 2x squared plus 2x minus 12. Yet I wrote 16. Minus 12 plus x squared minus 9. Difference of 2 squares. 2x squared plus x squared plus 2x, negative 12 minus 9. And subtract the 5 over. 3x squared plus 2x minus 26 equals 0. If the last one is any indicator, then this probably doesn't have rational solutions either, and that doesn't look factorable in any sort of way. 26 just has 26 times 1 and 13 times 2, and none of those will get me back to 2, even with the 3. So let's go ahead and do quadratic formula for this one as well. Let's do b squared minus 4ac, which is going to be 4 plus 12 times 26, 312, which is 316. 316, you can divide a 4 out for sure. I don't know if there's a bigger number, bigger perfect square, not 16. Let me start with this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, 316, if you divide it by 4, you get 4 times 75. 4 times 75 is 300, so 79. Yeah, 79 doesn't have perfect square factors. So x equals negative 2 plus or minus, that's 2 root 79 all over 6. When you divide these all by 2, you get x equals negative 1 plus or minus square root of 79 over 3. This is assuming that you can have those exact answers there, which I prefer. Exact's not rounded, at least for non-word problems. And those should not be extraneous because that's not a negative 3 or a positive 2. You're good there. Okay. What's on the other side? Error analysis is where we begin. Number 31. So number 31, describe and correct the error in the first step of solving the equation. So they're going for a common... Well, it's their choice. They didn't do the least common denominator. There are two things to me. Number one, they didn't do the least common denominator, which is whatever. That's not an error, but that's their decision. Number two, they didn't multiply this 1 by the same number. So that's the real problem here. Now, they found a common denominator. It's not the least common denominator. Not an error. Although not an error, they found a common denominator in 3x cubed, but it's not the least common denominator, which would be 3x squared. So I tend to, when I do this problem again, I tend to use 3x squared, just so you know. Now, that being said, what's the actual issue? They did not multiply 1 by their common denominator. Their common multiple, their thing, the 3x cubed that they needed. So let's redo the problem. I'm going to multiply by 3x squared. They have 5 over 3x plus 2 over x squared equals 1. Now, when they say the whole multiply everything by 3x, and I'm going to do 3x squared here, I'll do it in their terms, which means the distribution of. I know you haven't seen this in a while, maybe in the lecture portion, what have you. This, I'm already confused. 3 over 3 is 1x... I'm left with 5x here. So 5x plus, cancel out the x squared, 2 times 3 is 6, equals 3x squared. There's your setup. X can't equal 0, by the way, if we get that as an answer. Let's subtract 5x and 6 over here. I do not know if this is factorable. So we're going to give it a little test. Okay, 3, 5, I need to add 5. Minus 3 plus 2. That's negative 9. That doesn't work. I don't know if this is factorable. I don't think this is factorable. If it is, I might have made a mistake in my appearance on the numbers. Okay, so let's go ahead and try and solve this thing. We're going to get... the first step. Okay, I'm not going on from that. They didn't say solve it. They just said describe and correct the error in the first step. Okay, I'm going to move forward then. But this is what I'm going to do there. Okay, Number 32. By the way, I don't think that's factorable. Number 32. The first step here it appears there's the same issue. I can't tell because they're not showing parentheses around here, so there's no assumption that this is multiplying in both this term and the 4, but that 2x plus 5 times 3x, which is the least common denominator, by the way, is not multiplying into the 4. So it's not distributing into each term of the left expression. The LCD is not multiplying into every term. So it's kind of the same issue twice. This one is the least common denominator, though. So let's do that. We got 7x plus 1 over 2x plus 5 plus 4, that's over 1, by the way, equals 10x minus 3 all over 3x. So they're choosing to write it in this format. I'm going to write the 3x first, though. 3x times 2x plus 5. Boom. That distributes into kind of both of those. And then this is, that was their mistake the first time. Of course, I represent this differently, but it still gets the same effect as long as you know what you're doing with it through multiplication. So the 2x plus 5s cancel in this terminology, and you have 3x times 7x plus 1. You get 21x squared plus 3x. Here, this multiplies into all of these. 6x squared plus 15x times 4. That's 24x squared plus 60x. I'm trying to do that all in one step. And then this, this has a lot to do here. 3x squared. I don't know if we're supposed to do all this here, but 6x squared plus 15x times 10x minus 3. I think they just want you to fix the mistake, but I'm showing you how the fractions bust ultimately. I don't think I have to do all this. 60x cubed plus 150x squared minus 18x squared is plus 132x squared, and then minus 45x is over there. So that busts the fractions. I'm not going to do more because they only mentioned first step, so I'm just going to leave it like that. But the bottom line is 3x times 2x plus 5 needs to multiply with that as well. So I'm going to leave that there, and I think we're good to move forward. If they want us to solve, they should have asked to solve. Number 33, problem solving. You can paint a room in 8 hours. Oh, these questions are back. That makes sense. These are equations. Duh. They didn't show up in the lecture portion, though. I was bringing these up in the last section. You can paint a room in 8 hours. Working together, you and your friend can paint the room in just 5 hours. Let T be the time in hours your friend would take to paint the room when working alone. Copy and complete the table. So we're not solving? I don't think they're asking us to solve. They just say complete the table. Make sure everything's filled out. Maybe we have to do another one later in terms of figuring it out. Okay. So this is part. Well, there's a part B. I just realized that. So part A. Part A. Wait. Let T be the time your friend would take to paint the room. I don't like the 5 hours thing because we don't both, together we're 5 hours, but separately we're not. Oh, I see. 8 hours is here. So T is the time hour. So this is one room, and this is T hours for friend. Got it. Okay. Now, the work done, one room is the work done, I guess is the way that I would say it. I'm kind of confused with this time here. I don't like that that's there because that is for both of us together. I think that's how we do it. I don't know. I have to process what they're asking there because I don't like that they have the 5 hours thing there. Normally I wouldn't write it that way. Give me a second. Okay, the way that I see the problem now, they're saying how much could you get done in 5 hours despite the fact that you wouldn't complete it all. That's what they're showing here. Work done is work rate times time. Well, they're saying if you can do one room in 8 hours over the course of 5 hours, just multiply that, you'd cover, hours cancel out, you'd cover 5/8 of a room on your own is what they're saying. So it's kind of a, I don't know why they're doing the 5 hours, but this is how much work you can get done on your own over the course of 5 hours, whereas together you could, do more. Your friend can cover 5 over t, 5 teeths, 5 teeths of a room, like so. Which I guess kind of makes sense as far as now we need to add our work done together to get a total of that. So part B, explain what the sum of the expressions represents in the last column. Write and solve an equation to find out how long your friend to take to paint the room when working alone. I don't know if this is the way that I would set up the problem based off that 5 hours thing, because, well, I guess in one way this would normally be information you're trying to find itself. So maybe I would. I'm not sure. But if I, in 5 hours, can cover this much, and your friend in 5 hours can cover this much, and together we can complete a room, then this is the work done. Work done together when we add our things can be 1. So that's what the sum would mean there. So the sum of our work together, should be able to complete painting the room in the 5 total hours. I guess the reason why it looks different, like I said, than how I normally do this is normally time is what I try and solve for in the together part, but we actually know that information now. So maybe what they did is accurate. Anyway, so there's the sum, and it says, where is it? Write and solve the equation. So how long will it take your friend? So now it's just up to, doing what you want to do. Heck, I can subtract 5/8 from both sides, and now you get 5 over t equals 1 minus 5/8 is 3/8. So 3 over 8. Cross multiply, 8 times 5 is 40, and you get 3t, and you get t is 40 over 3, which is 13.3 repeating hours. That's 13 hours, 20 minutes. This is how long it would take your friend to do it alone. Me, I'm 8 hours alone. They're 13 hours, 20 minutes alone. Together, we could do it in 5 hours if we join forces. Number 34. So this is the same kind of question. They even give you the total time for them. So I think I now can use what they had on that. So number 34, you can clean a park in 2 hours. Working together, you and your friend can clean the park in just 1.2 hours. So I'm going to copy this table again. 1 park in 2 hours. Let t be the time your friend would take to clean the park. So 1 park in t hours is our rate. When you multiply by 1.2 hours, it shows how much we do separately as far as park coverage. So 1.2 divided by 2 is also 12 over 20, which reduces to 3/5. So I can do 3/5 of a park. Your friend could technically do 2/5 of the park, which I guess leads to what I mentioned with the 3/8. If I can do 5/8 of the room, my friend does 3/8 of the room. So that makes sense that we even write it that way. It actually does. That's actually nice. So I can do the same thing here. This is 1.2 over t parks, if you want to say it that way. Or that much fraction of the park completed. So that's part A. Part B, I think, is the same question. Express what it means and write and solve. So 3/5 plus 1.2 over t would equal 1 park total, because this is how much of the park I do. This is how much the park your friend does. My friend does. So again, the sum represents the... Are we cleaning? What are we doing? The total amount... Us cleaning the total park. I don't know. The park in total. Together. So I clean 3/5 of the park. My friend, over that time, if I subtract 3/5, they clean 2/5 of the park. So we got to figure out this over this equals 2/5 in terms of coverage. And I can cross multiply. 5 times 1.2 is 6, and we get 2t, and we divide by 2, we get t equals 3. So it would take 3 hours total for my friend. Okay. Let me see this other text. They sent a link. Responses to questions. Okay. Number 35. Open-ended. Give an example of a rational equation that you would solve using cross multiplication and one you would solve using the least common denominator. Explain your reasoning. All right. Cross multiplication. I would do ones with fractions. With a fraction equals a fraction. X over x plus 3 equals 3x minus 2 over 5. I'm not going to try and solve it, but it is a proportion. Now, I've done ones where I've turned them into a proportion because they were well primed and set up to do so. I want to do one that's less well primed and set up to do so coming up next right here. Let me kind of get into a different kind of problem here. Let's do, what did they say? LCD? LCD, least common denominator. Check out this one. Let's do, and this is, I don't know if the problem is going to work well, but 2 over x squared plus 6x plus 8 minus 3 over x squared plus 3x minus 4 equals 5 over x squared plus x minus 2. Now, what I did with this one, if I did it correctly, I don't care about the top, I just made those up. The bottom, this factors into x plus 4 times x plus 2. This factors into x plus 4 times x minus 1. And this factors into x plus 2 times x minus 1. Notice that each of these, and I wish we had some of these problems to do. This would kind of make a lot of sense to do this. Each of these has something that's shared. These both share an x plus 4. These both share an x plus 2. And these both share an x minus 1. So ultimately, they all need something that the other guy don't have. I don't know if it's a good kind of answer. It would be an answer. But that would be that one there. It is not a proportion. They each need, each denominator is missing a factor that another denominator has. That's one that I'm definitely not going for this, make a proportion out of it, something like that. That's the most, yeah. I want to do some of these, but it doesn't look like it's showing up yet. Open-ended number 36. Describe a real-life situation that can be modeled by a rational equation. Justify your answer. Well, you just saw a couple of them, and they are... It says justify your answer. Why did I write 5? I just don't know if I can write the equation well to begin with, but I'll just say... I think I kind of said these before. Al can wash a car in 6 hours. That's quite a while. Whatever, 6 hours. Bob can wash the same car in 8 hours. How long would it take them to wash it together? There's either that kind of problem, or there were the earlier problems of like, I need to raise my batting average to this, things like that. That would be a different example of one. These ones still take a little bit more to do. As far as setup goes, their table idea was good for Al and Bob. We could do how much work we need to get done. So distance, rate, and time. Their distances, they need to wash one car. One car, one car. Their time they take. Al takes 6 hours. Bob takes 8 hours. Again, that's a long time to wash a car. This is just, I should say wash the kitchen. Rate is distance over time. So we can do 1 over 6, one car over 6 hours, and this is one car over 8 hours. The idea behind this, however, is we need to find out what their rate is in a together stage. So when I add these rates, 1/6 plus 1/8, I should get a total of 1 over x, where we're trying to find out what value of x makes this thing work. And that would be a setup of rational equation. Not quite the same kind of rational equations you're used to, because common denominator can be had there. I'm going to try and just solve this one, just so we can, get the conversation had. Their least common multiple is 24, so I multiply this by 4 and this by 3. I get 4 plus 3 over 24 then. And that's 1 over x. 4 plus 3 is 7. So here we get 7x equals 24, and x equals 24 over 7. 24 over 7 is about 3.43 hours in total. I think I mentioned previously as well, these kinds of questions can also be solved. I believe it's the whole, you can do the a times b over a plus b thing. So 48 over 14 is the same thing as 24 over 7. So there we go. We get there again. So that's also very possible to do it in that way without setting up a rational equation. Anyway, there are a bunch of different ones that we can do, but that's just among them. All right, numbers 37 to 44. Determine whether the inverse of f is a function and then find the inverse. So f of x equals 2 over x minus 4 is our lead in here. We're going to turn f of x to y and then swap x and y to take the inverse. They don't ask us to graph unless that is their show. I'm going to multiply both sides by y minus 4. And in the process, I'm also going to divide both sides by x. What this does is it gets rid of things in the right way. So I can get y by itself again. And I can add 4 to both sides. I'll get y equals 2 over x plus 4, which is our inverse. Or inverse of f is 2 over x plus 4. This is a function. It is a function. There's no plus or minus x substituting any certain. Now, x can't equal 0. Here, x can't equal 4. That's neither here nor there. That doesn't matter. I can substitute anything for x, and I'm never going to get more than one y out from it. But the inverse is a function. Number 38. F of x equals 7 over x plus 6. Turn that into y. And if you notice last time, when I multiply by x plus 6 and divide by... Oh, sorry, I need to swap x and y first. But when I solve for y here, when I multiply both sides by y plus 6 and divide both sides by x, they switch places, like that. In subtracting 6 to both sides, I do get y equals 7 over x minus 6, or the inverse of f is 7 over x minus 6. This, too, is a function. No issues when it comes to that whole function matter. Listen, these will be functions unless you start seeing some plus or minuses flinging around the room. And I think so far we're good. Number 39. F of x equals 3 over x minus 2. Y equals 3 over x minus 2. Swap x and y. X equals 3 over y minus 2. I don't want to multiply by y yet just because that minus 2 is in the fold. I got to add this 2 over before I do anything like that. And then I can go ahead and multiply both sides by y, divide both sides by x plus 2. You get y equals 3 all over x plus 2 like that. So that's the version we're going to be writing, at least I believe. You know, you can do common denominator stuff, but I think that this just works itself out fine. This is for the better. In terms of getting y by itself, we're all good. So 3 over x plus 2, once again, totally a function. So this one looks backwards compared to the, not backwards. This one that it's just over this one value without any extra stuff and something on the side there, that looks like opposite of what these were from where they began. So notice how that looks and how that looks there. Maybe you can find a way of just writing the answer from what's there. I don't know. I wouldn't risk it, but the next answer might be what? 3 over x minus 2, 3 over x plus 2. Maybe this is 5 over the quantity x plus 6. Again, I wouldn't chance it, and not every question is like that, but I think that's what's happening. So I think my final answer will be, just based off that pattern, 5 over x plus 6. Let's see if we get there, which, by the way, would mean it's a function. But let's see if we get there. Turn this into y, swap x and y. Oh, yeah, totally. Subtract 6 from both sides. And multiply both... Oh, I'm sorry. This was a minus. Now we add 6 to both sides. And this is where we swap places. Multiply both sides by y, divide both sides by x plus 6. And we do indeed get 5 over x plus 6, which is a function. Sorry, that was number 40. I did not swap these. Okay, number 41. This is one where I think the book did something differently than I would have. And it's not that they did anything wrong. I went, oh yeah, I guess you could do that. Actually, I take it back. This one is different. Forget what I said. I thought this was a different kind of question, I believe. So anyway, y equals 4 over 11 minus 2x. I think we're good. Swap x and y. Let's go and solve for y. We're going to, yeah, this one's normal. We're going to multiply both sides by 11 minus 2y, divide both sides by x. We get 11 minus 2y equals 4 over x. 4 over x. Now, this takes a little bit more to do here. We have to subtract 11 from both sides. And we get negative 2y equals 4 over x minus 11. And then we'll divide both sides by negative 2. Now, when I divide by negative 2, that means this would go here and here. Okay, it goes with that 2x thing there, and I can simplify that. So this will be y equals, this is negative 2 over x, and this is plus 5.5. I don't know if you want to say plus 11 halves, plus 5.5. I'm not sure what your better way, I guess 11 halves is fine. Plus 5.5 like that, but that would be my answer for this one. Oh, inverse of. Is it a function? Yeah. Oh yeah, totally. And again, I'm not graphing these per se. Number 42. F of x equals 8 over, then I don't know if these questions will be like the ones in the lecture portion, unless they have other ones to do. But 9 plus 5x, there were other ones that they had at the time that I was like, all right, I'll do them that way. Maybe they'll show up later. Y equals 8 over 9 plus 5x. Swap x and y. Swap these places here suddenly. 9 plus 5y equals 8 over x. I'm going to subtract 9 from both sides. And then let's divide both sides by 5. Now in doing so, the 5 gets inherited down there and down there like that. So I'll get y equals 8 over 5x. Remember, the x is in the denominator. It's a rational function. Minus 9/5. Kind of weird numbers. But that's what we get. Also a function. 43 is where I question whether it'll be a function. Same with 44. I'm guessing they might not be, given that we might have to take a square root and a fourth root at some point. So get ready for some non-functions. The question is, what do they look like as graphs? I don't tend to graph them myself unless I use the graphing calculator, but I don't think these ones are functions. If we swap x and y, we got to solve for y here. And this is where, again, there's probably a little more to be had. I'm going to subtract 4 from both sides. So multiply both sides by y squared, divide both sides by x minus 4. You get y squared is 1 over x minus 4. And take the square root of both sides. You get y is plus or minus the square root of 1 over x minus 4. Now, I'm not going to try and rationalize the denominator, do anything like that. I'm just going to leave this all inside of a square root. Of course, I'm going to rewrite it in function notation, or inverse of the function notation, because I don't think this is a function. But I'm going to rewrite it like this. This one won't be a function. Not a function, because now when I substitute a value for x, keep in mind I can't substitute 4. I can't substitute 4, but 5, whatever. I'll get plus or minus square root of 1, which is plus or minus 1. I'm plugging in one x value and getting two different y values out, and that's not something that functions do. That's from taking the square root of both sides, and you get that plus or minus action. Number 44, I think, is the same. It's a fourth root. It's a fourth power, but that means we're going to be taking a fourth root, and even roots have that thing going for them. That should have said f of x to begin with. All right, we'll turn it into y and swap x and y. Let's add 7 to both sides. Swap places of those two guys right there. Again, hopefully you know mathematically why that's happening. I showed it a couple times, including the lecture portion. And take the fourth root of both sides. So this is plus or minus the fourth root of 1 over x plus 7. Again, not intending on rationalizing that or anything like that. We'll just leave it like that. So the inverse of the function is not a function, but this is still its appearance. This is its inverse right there. Not a function due to the plus or minus action. And the plus or minus action happened because we took the even root of a value. So the last two were not functions. I want to show you in the graphing calculator what these things would have looked like, and if they fail the horizontal line test, that makes them not functions. So right here, let's just do this last one. We did, let's look at the original. 1 over x to the fourth, and then minus 7. Looking at this graph, if it fails the horizontal line test, which it does right there, right? It's kind of a weird graph. I'm not going to talk much about it. other than horizontal asymptote at 7, vertical asymptote at 0, it fails the horizontal line test. That means its reflection piece would fail the vertical line test, which makes it not a function. Okay. So yeah, none of them were like the other ones that we did in the lecture. Number 45. The recommended %P in decimal form of nitrogen by volume in the air that a diver breathes is given by P equals 105.07 over D plus 33, where D is the depth in feet of the diver. Find the depth when the air contains 47% recommended nitrogen by solving an equation and using the inverse of the function. Okay, 47% they said in decimal form, so we need to substitute, let's do this is part A, substitute 0.47 into this thing and go ahead and solve it. You could also do 47 hundredths, but I reckon given that this is already decimal here and they said in decimal form, let's just use the decimal version. That's fine. So we got to find the depth of the diver with this one. We can multiply, I'll treat this as algebraic. Let's see, that's not the phrase. I'll treat this as differently as part B as I can, given how we're going to do the other version of the problem likely. I'll distribute the 0.47. 0.47 times 33 is what I got to do next here. The rest will be really in the calculator. 15.51. I'm going to subtract 15.51 from 105.07. And I get 89.56. Then I divide both sides by 0.47. That percentage we were talking about. So this is 190.55 feet, I'll say. I think it was feet, right? Depth in feet of the water. So this is how deep you are to have this much nitrogen, percent of nitrogen by volume. Okay, that was part A. Part B is getting D by itself first beforehand. So P equals... Let's do what we just did in the previous inverse questions. I can multiply both sides by D plus 33 and divide both sides by P. And I get D plus 33 equals 105.07 over P. Then I subtract 33 from both sides. You get D equals 105.07 over P minus 33. So here's a version of that equation, and now we substitute 0.47 in for P. So 105.07 over 0.47 minus 33. And when I do that, 105, I get the same answer. So the 190.55 feet of depth. Okay. They didn't ask which I'd prefer. I kind of prefer the second one. If I had to do it more than once, I would absolutely prefer the second one. But I felt like this was cleaner work for me to do. I could have maybe done that this way, but the distribution is what slowed me down here. That being said, this is fine. That works. It's just that if you got something by itself, then you just got to use the calculator the rest of the way. No more real algebra once you start off with algebra. Always trade-offs. Number 46. The cost of fueling your car for 1 year can be calculated using this equation. Fuel cost for 1 year equals miles driven times price per gallon of fuel divided by fuel efficiency rate. Okay. Last year, you drove 9,000 miles. Paid $3.24 per gallon of gasoline. Price per gallon. And spent a total of $13.89 on gasoline. Find the fuel efficiency rate of your car by solving an equation and using the inverse of the function. So let's do it this way first, and then finding the inverse after. Okay. I'm going to multiply both sides by x and divide both sides by 13.89. Let's do this now. 9,000 divided by... I feel like I'm doing the same thing both times, though. If I do the inverse, I'm going to... I don't have to think about it. So let's divide this by 1389. And I'm getting 20.9935, around 21. 21. 21 what? What is this? Fuel efficiency rate? That's, I guess it's miles per gallon. If we're dividing miles times price per gallon divided by miles per gallon, we would get price. Yeah, this is miles per gallon. MPG. MPG. That was one version of it, solving the equation. They said using the inverse of the function. If fuel cost is that part of the inverse, I'm going to do what I did here anyway. I'm going to swap them and do that division. So I can't really think of how these two problems are different. They're literally the same. I'm having trouble determining how I can make this an inverse without doing it the exact same way. Honestly, guys, I don't know what to say. Maybe my problem is I treated this one like an inverse the first time. Remember, in finding an inverse, I don't know what to do differently. I would still, even if I swap X and Y, whatever you call it, I do this exact same math. At least these ones appear different. I made this one here appear different from this one here. I can't make these two appear different because there's nothing added. It's just multiplied. Honestly, I don't really know what to say on this other than multiplying those things there divided by Y, the fuel cost. And then you plug that thing in. I'm sorry. I might have messed up doing the first one a little more like the inverse, but I think that's the way I would have done the problem anyway. Okay, number 47. 47 to 50, use a graphing calculator to solve the equation f of x equals g of x. Okay. My guess is, okay, let's do it. F of x equals 2 over 3x. G of x equals x. So we got to do, I wonder why they say use the graphing calculator. So we got to do 2 over, now we got to put 3x in parentheses. Just one of those things. And x over here. We got to find where these two intersect. So they intersect, boom, boom, at two different places there. Now, those two places, first curve. Sorry, first curve, second curve, guess. One point of intersection is negative. These are just decimals. Negative 0.8165. And I'm guessing it is positive 0.8165, given the nature of these. First curve, second curve, and guess. I got to get closer to this side here. Positive 0.8165. So where they intersect, we're finding the x values there, so plus or minus these two. Now they had to solve graphing. That's not to say you can't solve algebraically. I would have set 2 over 3x equal to x, multiplied by 3x, and get 2 equals 3x squared. Divided both sides by 3 and taking the square root. X is plus or minus square root of 2/3. Guess what you think? Guess what that is, right here. So I know I didn't rationalize this, but that becomes these two decimals. So okay. Number 48, and that's probably true of all these. It's like, well, it's easier to do without the graphing calculator, honestly. So number 48, f of x equals negative 3 over 5x, and g of x equals negative x. Oh, when it says use the calculator to solve the equation, they didn't say solve by graphing. I'm not going to solve by graphing. I can solve these algebraically. How about use the calculator to solve the equation? They didn't. I think they would say solve by graphing if they wanted that. So what I did here is what I'm going to do for the other one. So case in point, let's go back to that previous one. The square root of 2/3 is that 0.8165 value. Okay, so I'm going to use that for these other problems here. So let's set these two equal. Negative 3. At least you now know that you can find the points of intersection as well. But some people don't have, well, I guess that's the point of saying graphing calculator. If I multiply, but here's the thing. I don't need the negatives in this thing at all. They really mean nothing to me. But I multiply both sides by 5x, I get 3 equals 5x squared. Divide both sides by 5, you get that. And take the square root of both sides, you get x equals plus or minus the square root of 3 fifths. Now they said use the calculator, so this is where I'm actually going to use the calculator to do these things. So square root of 3/5. We have the plus or minus answer to this. So 0.7746. So x is about plus or minus 0.7746. Like that. Okay. Number 49. F of x equals 1 over x plus 1. G of x equals x squared plus 1. Set them equal. Yeah, let's do more algebra with this, right? These need x's to make common denominator. And now I can ignore the denominator as long as x equals 0 is not one of my solutions. And I get 1 plus x equals, that's x cubed plus x. Ooh. Oh, at least here the x's can cancel through subtraction, and I get x cubed minus 1 equals 0. Now, here's the thing. You could add 1 and take the cube root of both sides, which I guess is fine. What I'm curious about with this one, though, is this is also a difference of 2 cubes. This factors into x minus 1 times x squared plus x plus 1. No, minus x. Wait, hold on. X squared, yeah, plus x plus 1. Like that. And this one would give you x equals 1. And this would give different answers there. I feel like did I misrepresent something there? X cubed plus x. Give me one moment. Let me make sure we're good. Okay, I just realized. Okay, because I was looking at this problem here and I said if I plug in 1, 1 plus 1 is 2 and 1 squared is 1, and that's not right. Here's the problem. This is not x squared. This is x squared plus 1. So I made a mistake. Let me go back. That shouldn't say plus 1 here. That should just say x squared and x cubed. There we go. Okay, let's do this again. My bad. I just didn't copy down the problem right. The next problem says x squared plus 1 right there. That's the point of having this circle here. Why can't I see that? Anyway. All right, so now we get a common denominator. We have this. Now I have, ooh, this is where I might want to solve by graphing. Okay, they win. I'm using the graphing calculator on this one. So, wait. Yeah, I'm using the graphing calculator. I'm thinking rational root theorem, but I don't think that works. Okay, so this has x cubed minus x minus 1. And I want to see when these equal 0. So I'm doing it a little differently. Maybe now the book's telling me this is how you should have done it to begin with. But I'm going to find the 0 in between here, which is the same way as setting those equal to each other to begin with. And I'm getting 1.3247. And there's just one answer. All right, graphing calculator used a little bit more on that problem. All right, number 50. Let's copy down the problem correctly this time. You have f of x equals 2 over x plus 1 g of x. And I'm going to attempt to solve algebraically first. That is x squared plus 1. So set these equal. And get some x's all up in here. So now I'm going to have 2 plus x equals x cubed plus x. So now it is kind of like that other problem. X is subtracting, you get x cubed minus 2 equals 0. This is not a difference of 2 cubes, so it's easier to just represent by doing this and taking the cube root of both sides. And that's just cube root of 2. It's not plus or minus cube root of 2. But just the cube root of 2 itself. So let's take the cube root of 2, and we will get, oops, cube root 2, 1.2599, almost 1.26. But I've been rounding to 4 decimal places, so I'm going to continue doing that here. No plus or minus, just one answer there. Okay, number 51. Golden rectangles are rectangles, The golden ratio, for which the ratio of the width w to the length L is equal to the ratio of L to L plus W. The ratio of the length of the width for these rectangles is called, yes, the golden ratio. Find the value of the golden ratio. I'm trying to copy and paste. I don't know why I'm trying to copy and paste a rectangle. Maybe because I believe that this actually is in the golden ratio right now. So I want to demonstrate something with it. Find the value of the golden ratio using a rectangle with a width of 1 unit. Okay. In a different explanation of it, and it is a different explanation because I'm also going to shrink this here. A different explanation is this. If I drew a square within here, this new rectangle right here has the same ratio as this rectangle right here. When I draw a square within here, this rectangle has the same ratio as this rectangle and this bigger rectangle. When I draw a square within here, this rectangle has the same ratio as this one, and that one. I don't know if that's true or not based on, I don't know if this is to scale, but let me try that. Let me try and take this one here and shrink it. This is not the problem, by the way. But let me try and shrink it. I have to rotate it as well. And see if it matches this guy here. Yeah, pretty much. So that's in the golden ratio. And if we shrink that one, rotate it again, shrink this one, you know what happens? My software sometimes snaps this thing wrong anyway, so I'm going to pretend like it was. And then when I go to this one and shrink it again, same thing. It maintains that ratio there. So that's the idea of the ratio. Anyway, how are they asking us to do this? Let's do some, let's get rid of some of the things I was drawing. I was just fooling around so you can understand what it's actually saying. They actually said it the other way. They said that the ratio, the length is equal to the ratio of L to L plus W. That means we're going to have to add an L to the W. So I have to like bring this upward. Here, I'm going to shrink this now. I have to bring this upward and make this a bigger version of this rectangle. Basically, I need to make it, so I guess what I explained is good, because now what I'm going to do is I'm going to make this size. This is not required for you to do. This is just the visual explanation of what we're doing. I'm going to take, I'm going to take this and grow this until the length of one becomes the width of the other. Right? So this is the idea here. So this is what we're doing. We're expanding upward. Like that. This is now L plus W, because this is L. This there is that same length as that L right there. So this is golden ratio variety. They said find the value of the golden ratio using a rectangle with a width of 1 unit. Okay, here's what we're saying. If these are similar rectangles, then that means that when I divide width by length of this original rectangle, that's the same as dividing this width by this length. And that width is L, that length is L plus W. Now our W is 1, so we're going to go ahead and say 1 over L equals L over L plus 1. Find the value of the ratio. So let's solve for L and then do things off of that. We can cross multiply. We get L squared equals L plus 1. We can subtract, I didn't subtract. We can subtract L and 1 to this side of the equation. And let's solve, that's not factorable. Let's solve using quadratic formula. L is negative b, opposite of negative 1 is positive 1, plus or minus the square root of b squared minus 4, I know I didn't do discriminant first, ac, all divided by 2a. So it's L equals 1 plus or minus negative 1 squared is 1, plus 4 is 5. So square root of 5 all over 2. Length can't be negative, so the 1 minus 5 don't work out here. This will just be L equals 1 plus root 5 over 2. And was width, there's just 1 unit. So this many units for length. Length divided by width is this divided by 1. So therefore, the golden ratio is this value. That's 1 plus square root of 5 all over 2. Now that approximates to something. I think it's around the 1.6 range. So that means the length needs to be about 1.6 times the width. That's not exact. Clearly this is exact. But But the length needs to be this many times larger than the width for the golden ratio to be what it is. That should be the answer. Number 52. How do you see it? Use the graph to identify the solutions of the rational equation. Here, this equals this. Explain your reasoning. Well, it's the point of intersection. Now, given that the blue is a rational equation, I mean, the red, well, okay, I'll talk about the red a little more in a little bit. Given the blue is a rational equation which has that kind of appearance to it, it looks like listen, it has some sort of horizontal asymptote. It looks like it's right here. The point is, this blue part right here will never eclipse that 2. It'll never come up to 4. So the only time they intersect is right here at x equals -3. It's the only place they intersect. So x equals -3. Point of intersection. It's the only point of intersection we're going to see. There's not another one. Now, here's the other thing I wanted to bring up. You might wonder why this red equation, which appears like a rational equation, becomes a line, a constant, because x minus 1 over x minus 1 cancels. But then you're wondering, well, why is it written? That does mean that there's a hole in this equation. I know we didn't get to graph with holes, but there's a hole at x equals 1, which means if this is where they intersected, there wouldn't be a solution, because this can't divide by 0. So if this is a hole right there, that means there's no defined value there, but it approaches 4 to the left and right of that value, which is interesting. Anyway, that's the other thing I wanted to bring up. Numbers 53 and 54 say, find the inverse of the function. These are the kinds of questions I was bringing up from the examples. Find the inverse of the function. Hint, try rewriting the function by either using inspection or long division. Okay, I don't plan on using inspection. It's not terrible. It's just I did more in the long division front, but even I don't do that personally. I'll do it from what they're stating. You know what? We'll use long division once. I'll not even use synthetic division. I'll do what they say here. I'll use long division once, and I'll use inspection once. So, first of all, long division. It's not that long. We just do this once. X goes into 3x 3 times, and you multiply that, you get 3x minus 12. Subtract those, and you get a 13. So we get f of x equals 13 over x minus 4 plus 3. I'm glad I'm not graphing it, just because that 13 is a little weird. But we are finding the inverse. So set this y, and then swap the swap the x and y, and then solve for y again. So kind of low on room here, but I'm going to subtract 3, and then we'll swap these places. Multiply both sides by y minus 4, divide both sides by x minus 3, and then add 4 to both sides. And now we're getting the inverse is 13 over x minus 3, and then plus 4. That's one version of it. That was without a common denominator, but that still works as an inverse to that thing. Now, if you wanted a common denominator, 4 needs to multiply by x minus 3 over x minus 3, in which case you would get 13 plus 4 times this x minus 3 all over x minus 3, and 4, that's 4x minus 12, and 13 minus 12 is 1. So you would get 4x plus 1 all over x minus 3. Here's another version of it. And that took a little bit longer to get to that stage than I would have liked, just because we had to do the long division to get there to begin with. So I'm curious as to why they kind of represent it that way. I'm sure that they have their reasons. And inspection would do the same thing for us. So number 54, yeah, I don't know. I'm not as much a fan of doing it these ways. So number 54, we get f of x equals 4x minus 7 over 2x plus 3. By using inspection, now, I'll talk about it in a minute. By using inspection, let me write it as y now. We'll get y equals, and we got to multiply 4 with 2x plus 3. Okay, 4 times 2x plus 3 is 8x plus 12. So we'll get 8x plus 12. No, you want... I could multiply 2 I don't need to make it that big. I could multiply 2 with 2x plus 3 to get 4x plus 6. That's fine. Now we'll do minus, see, this inspection's harder. I got to subtract 13 to make that become a minus 7 again. Now we can split that up by taking out a common factor of 2, dividing this by its own 2x plus 3, and the negative 13 splits up, gets its own 2x plus 3 there. And so now you have y equals negative 13 all over 2x plus 3, and then plus 2. So there's this. This is not the inverse. This is just using inspection to get this single x by itself here. Now we get to swap x and y. We'll subtract 2 from both sides. We'll swap the places of the y quantity and the x quantity. 2y plus 3 equals negative 13 over x minus 2. And then we'll subtract 3 from both sides. And then we'll divide both sides by 2. You get y equals negative 13 over. When I distribute the 2 here, it'll be 2x minus 4. And this is minus 3 over 2. That's a lot, and it's not something that I prefer as an appearance of an answer personally. I want to kind of do something else with that. So as far as this, I probably want to get a common denominator. Let's do this actually. Let's rewrite this as 2 times x minus 2, like that. Now to get a common denominator, I have to multiply this by x minus 2 on top and bottom. And then we get, and by the way, I'm going to write this as inverse now. Inverse is negative 13 minus 3x plus 6 all over 2 times x minus 2. I might as well distribute that now as 2x minus 4. And that is going to be negative 3x minus 7 all over 2x minus 4. So there's the inverse. I don't prefer those ways. I wasn't even talking about inspection. I don't prefer the way of long division of doing that. There are other ways to do it, and the issue, this is what I was going to bring up, the issue with doing it the other way is when you swap x and y, you get y in 2 different parts of the fraction, and people don't know how to do that. I want to teach it and show you how to do it, but they didn't really seem to be a fan of that. 55, abstract reasoning, says find the inverse of rational functions of the form here. Verify your answer is correct by using it to find the inverse of exercise 53 and 54. I'll tell you what. This might be where I get to do this here. This is going to look a little weird because this is all letters, but this hits home the exact thing that we're going to have to do. To find the inverse here, you got to swap x and y. But the problem is you got y in both parts of these. Here's what you do. You get this up. You multiply both sides by cy plus d, but you keep the x there. So x times cy plus d equals ay plus b. I'm going to distribute this x into here. My goal is to get all y terms on one side of the equation, but I can't do that until I have everything kind of written where they need to be. Cx times y plus d times x, and write everything alphabetical, equals a times y plus b, like that. Now I'm going to subtract the ay on both sides. I want these two together on their own side of the equation. And then I want b minus dx, any non-y terms, be on this side because I want to factor y out. And I get cx minus a. And here I got b minus dx. Now I can divide both sides by cx minus a. And I get y equals b minus dx over cx minus a. Like that. This is the inverse. Oh, let's see. They never wrote f of x. So this is the inverse version of that. Now, they said, verify your answers correct by using it to find the inverses in 53 and 54. I don't know if they mean just plug these numbers straight into here and see that it worked out, but if we did, number 53 basically had, for ax plus b over cx plus d, it had ax plus b over cx plus d. So your a was 3. Let's see, that's just hard to see. Your a was 3, so this would be here. Your b was 1. Your c was 1. And your d was, is that right? Oh, I'm sorry, c is down here. Your c, I have to look right here. Your c was 1, and your d was -4. We're subtracting -4, which is plus, so plus 4x. So is this the answer we got? 1 plus 4x over x minus 3? I probably would have written 4x plus 1. Yeah, 4x plus 1 over x minus 3. So that's the same. And the other one, number 54, is a would have been, I guess we have to write y equals. A would have been 4. B would have been -7. Where does that go? Where did I write it? Oh, B. -7. I keep looking at that. Whoops. I keep looking at this, and I should be looking at this. C would have been 2, and D would have been 3. So did we get -3x minus 7 over 2x minus 4? I believe so. Yes, we did. So those are confirmed. Now, I plugged numbers into there, and that's kind of weird to do. What I'd prefer to do is this, and I do want to show you guys these. I'm going to redo numbers 53 and 54. Timeout. I'm going to make this a timestamp. So, ready? 3, 2, 1, go. I'm going to redo numbers 53 and 54 in a way that I prefer doing. Right here. So, in terms of finding inverses, based off what you just saw from the previous problems, I think this opened up, based on number 55, it opened up a window of opportunity for me to go back and do these in a different way. So I'm going to set y equal to these, and I'm going to swap x and y. Now what this does is this does bring multiple y's in the fold, and I got to solve for it. So I'm going to do it by multiplying both sides by y minus 4. X multiplies by the y minus 4 here. I'm going to distribute x into here, like that. And I want to get y terms on one side of the equation. So I'll subtract 3y over, and I'm going to add 4x over. Y is a common factor right here. And I can divide both sides by x minus 3, and I get y equals 4x plus 1 over x minus 3. Or that's the inverse there. So when you compare this, and it's up to you, this is just the way I prefer doing it. When you compare this to the way we originally did number 53, using, it didn't matter, long division, synthetic division, inspection, all this kind of stuff right here. We had another version that looked like that. That's up to you. But we got to there eventually. It took a little bit more time in my book. Not really as much a fan. Number 54, done a second time, remember. We're doing them again. 4x minus 7. I wonder how I'm going to write these in the timestamps. If I write them 53, 54, 55, 53, 54. 2x plus 3. All right, that's the problem. Okay, so y equals, swap x and y, and now solve for y by distributing. If you notice last time we multiplied 2y plus 3 up here, so I can distribute x into there right now, like that. We want all y terms on one side of the equation so we can factor out y as a common factor. So subtract 4y from both sides, like that, and subtract 3x from both sides. Factor out the y now, and you get 2x minus 4. And then divide both sides by 2x minus 4, and you get your inverse, is negative 3x minus 7 over 2x minus 4. We've seen this problem a couple times now that we do know that that is the answer, so I'm going to leave it like that. Okay, and I already did 55, so I'm not going to do that one again. All right, 3 more questions to go. Number 56. Thought-provoking. Is it possible to write a rational equation that has the following number of solutions justify your answers? I don't know if we have to come up with ones or something like that, but A is no solution. Yeah, we saw a no solution case. Yes. I don't know if I want to make different ones, but we can have no solution. We have to get an x value that is a solution that we can't divide by. Like x equals 0, but we can't divide by 0, that kind of thing. I can do one that we had before. I don't have to make one up if I already have one here. It's hard to think of problems like this off the top of your head, especially, you know, when you're in the midst of like doing all the other problems. So look at all this work I've done, man. Like these ones here. This was an example. So I'm going to copy and paste this one over. That had no solution, right? So you can see it's not necessarily the easiest thing to come up with these answers. You know, like do them. Like come up with problems that make them work. All right, so here, whoa, I spent all that time copying that over. It didn't even copy over. Hold on, let me pause and do that again. Okay, dragged it over. So that is part A. Part B. Exactly one solution. I'm sure I can make up something like this. I don't know how none of these won't work. But yes. 2 over x plus 3 equals 7 over x. Subtract 2 over x from both sides. 3 equals 5 over x and x equals 5/3. That's one solution there. Two solutions. We have had two solutions. Now quadratics have to be introduced in the fold, and I don't know if I'll do this well or not. If I do a proportion, it might make it easier. So something like x over x plus 1 equals 2 over x minus 4. And here, let's see, I don't know. This isn't necessarily factorable. Hold on, I might change these. Give me a second. X squared minus 4x equals 2x plus 2. If I say, okay, so that's not really factorable. Let's do this. Let's do an x plus 4 here. Oh, I don't think that'll have two solutions if I do that. Let's do a 5. I have to think about this. X squared minus 5x. And let's do a 7x minus 3. Let's try this. 2x minus 6 when you distribute, right? So cross multiply, distribute. Subtract this over, you get x squared minus 7x. Add the 6 over, plus 6 equals 0. And this becomes x minus 6 times x minus 1 equals 0. And there you get x equals 6 and x equals 1. And those are not extraneous, right? Those would work there. So, hey, I made a problem. It was proportions, but I made a problem. Part D, infinitely many solutions. Yeah, as long as they are equations that are the same on both sides. It's just one's like a bigger version of the other. So if I had 2 over x plus 3 equals, and let's say I multiplied these by 5, and I get 10 over 5x plus 15, right? This is literally 5 times larger than that. What would eventually happen here is, I mean, there are a lot of ways you can come up with what you do here, but you listen, let's cross multiply. 2 times 5x plus 15 is 10x plus 30, and 10 times x plus 3 is 10x plus 30. When we subtract 10x's from both sides, you get 30 equals 30, which is infinitely many solutions. Infinitely many solutions just happens when the left side and right side are actually the same equation, even if they don't appear that way. Maybe you need a common denominator. Maybe you need to get the, whatever. But yeah, that's that. All right, number 57. Critical thinking. Let A be a non-zero real number. Tell whether each statement is always true, sometimes true or never true. Explain your reasoning. For the equation 1 over x minus a equals x over x minus a, x equals a is an extraneous solution. That's always true. No matter what, when you substitute a into that thing, you're going to be dividing by 0. Always true. Division by 0 is never allowed. Just straight up. When you substitute a in there, you are going to get 0. That's what's going to happen. Now that is part A. Part B. The equation 3 over x minus a equals x over x minus a has exactly one solution. I see no reason why that would always be true. It's a sometimes case. Because you create a quadratic, I have to make sure that it's ever even true. If you have says exactly one solution, when really what I'm looking at is the fact that this would more often than not have two solutions. Oh, wait, I'm sorry. These are both x minus a's, right? All right, x equals 3. There it is. There it is. Now, the problem is, I forgot they're the same denominator. The problem is, x equals 3 would not work if a is 3. So I guess x equals 3 would be the one solution, with the exception of when a equals 3. So this is sometimes true. It is true in every case except if a equals 3, in which case there are no solutions. All right, part C. The equation here has no solution. 1 over x minus a equals 2 over x plus a plus 2a over x squared minus a squared. I feel like I need to do more work on that to figure out what's going to happen. So 1 over x minus a equals 2 over x plus a. And I'm well aware that what I'm seeing here is a difference of two squares. So this is x minus a times x plus a. So let's go for, extra work. Common denominators. Like that. And we're going to now get x plus a plus 2x minus 2a. No, I'm sorry, this is an equals. X plus a equals 2x minus 2a plus 2a. Now here you get cancellation. X plus a equals 2x. If you subtract x from both sides, you get x equals a. X equals a ain't allowed because that'd be dividing by 0. So this is extraneous. That means no solution. What was the question? That this has no solution? That's always true. Because your only solution, so always true, the only solution that you get becomes extraneous. So that's with some work being done on there. Okay. Final question, number 58. Your friend claims it is not possible for a rational equation of the form x minus a over b equals x minus c over d, where b and d don't equal 0, to have extraneous solutions. Is your friend correct? Explain your reasoning. I'm guessing x is the variable and b and d are numbers, right? Just non-zero. It's not possible for a rational equation of this form to have extraneous solutions. Is your friend correct? My friend's correct. So 58. My friend is correct. There are no variables in the denominator. There aren't any variables in the denominator, which is the only way we would have division by 0 forms of extraneous solutions. See, that's what we're looking for. But there are no variables in the denominator. So without that, there's no concern. B and D aren't variables. Those are numbers. They're non-zero values, I suppose, is the way we're trying to say. Okay. Guys, that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. We finished the chapter, and we're going to do chapter review. I mean, we have chapter review and chapter test and cumulative assessment still to do, but we finished the information, so we'll see how those ones look. It might be a lot of work to be had. We'll see. All depends. I hope that everything I did with the different kinds of ways were helpful to you, not hurtful. My goal is to give you a lot of different strategies. Look how hot it's going to be here. My goal is to give you a lot of different strategies and that you can use which ones make most sense to you for any particular problem. Guys, thank you so much. Take care. I'm going to see you in the next one.